Okay, number 49. We've got a machine carrying a 4-kilogram package, and they give us the initial position in unit vector notation in 3 dimensions at time equals 0 to a final position, also given in unit vector notation in 3 dimensions, 12 seconds later. There is a constant force applied by the machine on the package, and that's also given in 3-dimensional unit vector notation. For that displacement, find the work done on the package by the machine's force and the average power of the machine's force on the package. So first of all, they give me the final position and the initial position. So the displacement then is d final minus d initial. So when I do that, I see that it moves 7 in the x, 11 1/4 in the y, and 7 in the z. If you think about your 3-dimensional coordinate system, x, y, and z are all perpendicular to one another. So that means forces in the x do no work in the y or the z because they're perpendicular. Likewise, forces in the y do no work in the x and the z, and forces in the z do no work in the x and the y. So all I have to do is multiply in the x the force times the distance. That gives me 14 joules of work done in the x direction. 11 1/4 times 4 is 45 joules of work done in the y direction. And 7 times 6, 42 joules of work done in the z direction. Work is not a vector, so we just simply add them up. Those 3 added up gives me 101 joules of total work done. Then the power, of course, is the work divided by the time. So 101 divided by 12. You notice here, it doesn't matter if you do the power in the x, the power in the y, and the power in the z, and add them up. You'll get the same answer as if you use the total work divided by the time to give you the total power, or the average power, I should say, 8.4 watts.